Everybody, it's video notes 5.1, chemical reactions and enthalpy. Fancy word for heat. We're going to look at chemical equations and describe the symbols and stuff. We're going to look to see if a reaction's endo or exothermic, and we're going to draw energy diagrams and calculate enthalpy. So here we go. Chapter 6 in the book does a really good job with chemical reactions. So read it. But then do self-check 6.3 to see if you're understanding stuff. Okay, so how do we know a chemical reaction has occurred? We have an unexpected color change, heat is produced, it precipitate forms, it's a solid. Okay, here let me show you what that means. I'm pouring two solutions together here and you get this chunky solid. A gas is produced or an odor is produced. Those are some signs of chemical change. So what is a chemical equation? Well, there's one right there. So it's an equation that uses symbols to represent a chemical reaction. So this is what's happening, and here's the reactants, and here's some other stuff, and here's some products. Okay, so reactants turn into products in a chemical reaction. So where are reactants? What are reactants and products? The reactants are substances that are used up in a chemical reaction. There's a starting material. Products are made in a chemical reaction. So remember that the arrow points to products. So label them in this diagram. Okay, so this is a chemical reaction. Here are our reactants. Ooh, reactants. And here are our products. Okay, so you could have one, you could have more than one, you could have more than two, but the arrow is like an equal sign. So this turns into this. All right, so there's some symbols that you're going to have to know. If you see a G in parentheses, it's gas, liquid, L for liquid, S for solid, AQ for aqueous. The plus sign on the left-hand side of the arrow is reacts with or and on the right side of the arrow it is also produces or and. So if a solid forms or precipitate forms, you can use a down arrow or you can use a solid. If you see it, so that can only be used in the products. If a gas forms in the product, you can use G for gas, or you can use an up arrow. The arrow, you might see a short one, you might see a long one. That means to produce, so or yields. And then if you see substance above the arrow, it's a catalyst. Okay, so let's try this equation. Oh, actually, let's go back here and see if we can label some more stuff. This means it's solid. This is a catalyst. And this is a solid. And this is when we can use the up arrow to mean gas formed as a product. Okay, so here's an equation. Let's put it into words. We have to know what kind of compound it is. It's an ionic compound, so in the same manner. So solid, copper, oxide. But wait, is copper and always or a Roman? It's a Roman. It's a -2, it's a +2. So it's solid copper 2 oxide reacts with, that's what the plus sign on the left-hand side of the arrow means, liquid water, which water means liquid, but I was emphasizing that L means liquid. But if you say water, you just mean liquid. To produce, that's what the arrow means. We have aqueous or solution of aqueous, solution of copper hydroxide. But wait, is copper and always a Roman? Well, it's a Roman, so this is OH is a -1, but there's two of them. Copper must be +2. Copper 2 hydroxide. So we just translated the chemical equation in symbols to word equations. So this is a symbol equation, and this is a word equation. Okay, can we do the reverse? Well, yeah, we could take the words and write a chemical equation. So this is solid magnesium. Solid magnesium. So you got Mg, you got solid. Reacts with, that's the plus sign, oxygen gas. And then we say to ourselves, oh, that's one of those 7 diatomics. We have to put 2 next to it to produce. So we're talking arrow, solid magnesium oxide. Well, magnesium is a +2 from the periodic table. Oxygen is -2. So that's MgO. So we got to put that all together. So we have solid magnesium reacts with oxygen gas to produce magnesium oxide. And that's a solid. Now, I'm going to put in coefficients here. I want you to know that coefficients can exist, but we'll balance equations later. Okay, so this is the word equation, and this is the symbol. You have to be able to translate. Okay, so there's 7 diatomic elements. We just ran up into one of them for as oxygen. Or remember the 7, make a 7, point to hydrogen. Nafkubrich, or some people like Honkubrich. Either way, you have to know all 7. Okay? All right, so to review a balanced equation, these numbers in the front of the symbols are called coefficients. The numbers below are called subscripts. Right? Things on the left side of the arrow are called reactants. Things on the right side are products. And then states of matter are put in after states of matter. So that's what you need for a chemical reaction. Okay? All right. So why do these reactions happen? What's the relationship between stability and energy? Well, lower energy equals more stable. So a chemical reaction will usually happen, or a lot of times it'll happen for one reason at least, so that the products are more stable or lower in energy. Law of conservation of energy says that energy is not lost or gained. No energy is lost or gained. In a chemical reaction overall. In a chemical reaction. So we have to be able to account for all the energy along the way. Okay, so why are some reactions explosive? Well, if they can lead to a really, really, really stable product, then they could be explosive. If they release a lot of energy quickly, then they can be explosive. Okay, so how do we talk about this energy? Well, when things are reactants, those things have chemical bonds that hold them together. When things are products, they have chemical bonds that hold them together. But for reactants to turn into products, you have to break bonds. All here, you have to break bonds and then make new bonds. So in order to break the bonds, you have to add energy in. So all chemical bonds have energy stored in them. Okay, and if you want to break those chemical bonds, you have to add energy in to break the bond. And so these numbers here are the bond energies for some different kinds of bonds that we're going to be looking at. So if you see here, this is the chemical bond. Right? So you have two things that if they're too close together, they have high energy. But when they form a chemical bond and have the right distance apart to be the most stable, then energy is released. So energy is released when bonds form. Remember that energy is always released when bonds form because the bond is more stable than the things by themselves. Right? But if you want to break that bond, you have to add energy in to get that bond to break and move those atoms away from each other. So energy is absorbed when you break bonds. So that's positive bond energy. Energy is released when bonds form. That's negative bond energy. Releasing is negative. Now, no energy can really be negative. You can't have energy below 0. It just means that it's less energy. Okay. So bond energy and stability. So we'll look at these two diagrams. Which reaction is more likely to happen and why? So when we said over here, stability and energy, lower energy equals more stable. Okay. So if we look at these energy diagrams, which one has lower energy in the products? Well, this one has lower energy in the products, so this one is more stable. This is called an exothermic reaction because the products have lower energy than the reaction. This is called endothermic reaction because the products have more energy than the reactants. Okay, which one's going to be most likely to happen just based on energy? This one, because this is lower energy when you're done with the reaction. Okay, so two kinds of energy diagrams here. One is for an exothermic, one is endothermic. Exo means release, right? And then endo means absorb. But notice that this reaction, you still absorb energy first to break bonds and release energy when bonds form. So this is breaking bonds, absorb energy, and then always energy is released when bonds form. Oh, this is a new. What did I just spell? I just spelled barf. Okay. Because when bonds are breaking, it absorbs energy. Breaking bonds absorbs energy. And anytime new bonds form, energy is released when new bonds form. So breaking absorbs. So that's always going to be adding in energy and energy. And then energy is released when bonds form. And form bonds. Breaking bonds absorbs energy and release when forming bonds. Energy is released. Energy is released. Wow, can you read that? Okay, so you always got to go up first. So how can we calculate that? Well, when we do calculate, it's called enthalpy. It's the heat of the overall reaction. So we get a total of the energy absorbed to break the bonds and the total energy released when bonds form. And overall, we have the heat of the reaction. Okay, so what is the energy change for the formation of water? Okay, so we have to look at this and we see a 2 there. So what does that mean? That means 2 of those molecules. There's a 1 there, and then oxygen is diatomic because it has that and it's got a double bond. And then water, so we have to be able to see the dot structures a little bit here. Why am I drawing 2? Because there's 2 of them, it says right there. Okay, so if we want to know the energy change for making water form, we have to break these bonds. Okay, so breaking these bonds means, well, there's 2 of them, so we have to break both of those. We have to add in 436 kilojoules per mole of energy. And then we have to break those bonds, so we have to add in, let's see, 499 kilojoules per mole of energy. Right. So all of that energy is 1,371 kilojoules per mole of energy. All right. That has to be added into breaking. Now remember, energy breaking absorbs, so we have to add in energy is released when bonds form, so that has to be released. So there's 1 OH, 2 OH, 3, 4 OH bonds, 4 bonds of OH, that every time one of those forms, 463 kilojoules per mole of energy is going to be released. So I put the negative sign on it because releasing means negative. So 4 times that is 1,852 kilojoules per mole of energy. So what does this all mean? Well, it means that to go uphill, we're going to need to put in 1,371 kilojoules of energy. To go downhill, we're going to release, so breaking the bonds is going to take that in. Making the bonds is going to release 1,852 kilojoules of energy. Right? And so if we say 1371 plus negative 1852, we are going to get negative 481 kilojoules per mole of energy. And so then this difference right here is going to be our negative 481 kilojoules per mole of energy. Okay, I'll do that again on the next screen. But to calculate, all right, so here's all of the energy we have to add in to break that. Here's all the energy that gets released when the new bonds form. Okay, and I calculated that. And so we can say that on this side of the reaction, there's going to be 481 kilojoules per mole. So I'll just leave this. I'll leave this kilojoules per mole of energy. Okay. So why did I put it on this side? Because we had to add in 1371 over here. We took 1371 kilojoules to break all that up. And then we released 1852 kilojoules. Right? And so the difference is the net energy on this side because that also is released. So if we were to draw an energy diagram, we would label it. We'd put an R for reactants and a P for products. Right? You have to add in 1371. Right? You don't have to label this part. And then you'd release 1852 for products. And so then this is the delta H, which we calculated on the last slide. And that's going to be here, delta H, and it's a negative 481 kilojoules. Okay. And so this is what kind of reaction, endo or exothermic? This is exothermic reaction. How do we see it in an energy diagram? Because the products are lower. How do we see it in a balanced equation? We see the energy on this side. How do we know to put it on this side? Is because when we take the bond energies, there's an extra 481 kilojoules released as the bonds form. Okay? All right, so here's one that we're going to try in class. I want you to know that this is going to look like this. Right? It's C3, CH3, CH2, CH3, right? And then oxygen is O2. But remember, there's 5 of them here. 4, 5. And then CO2 looks like this. And then H2O still looks like H2O, but there's 4 of them. This one's a little more complicated because there's a lot more bonds going on. But you could do it the same way. I'll leave that here. You're welcome to try it. And we'll do that one in class. And then after we do that calculation, you should be able to draw an energy diagram for it. Okay. So just remember to read chapter 6 and do the self-check 6.3c. And then hopefully you can describe how to, the symbols and stuff in a balanced equation. You can see if the reaction is endo or exo from an energy diagram, sign of H, or calculating the bonds, bond breaking and forming energies. And that's calculating delta H. So peace out, peeps. See you in class.